Hi, this is S. Lakshmanachari, working as Assistant Professor in Department of Cybersecurity, Institute of Aeronautical Engineering, Hyderabad. In this lecture, we are going to discuss inter-process communication and synchronization. So, inter-process communication. So, communication means transferring of information from one place to the another place, or exchange of information. So, that is nothing but communication. So, in inter-process processor communication, that means this is using in multiprocessor systems. So, in multiprocessor system, we are having more than one processor. That means we are having 2 or 3 CPUs inside the system, so that the communication that established between the computers in a multiprocessor system, that is called inter-processor communication. So the various processors in a multiprocessor system that must be provided with the facility for communicating with each other. So if you consider a multiprocessor system, so we have multiple CPUs, so multiple processors or controllers. So in multiprocessor system, one processor can communicate with the another processor. So a communication path can be established through the common input-output channels. So in a shared memory, the multiprocessor system, the most common procedure is to set a portion of memory that is accessible to all processors. So here, so you can see the multiprocessing architecture here. So here you will see multiple CPUs are there. CPU 1, CPU 2, 3 and CPU n. So like that we can connect n number of CPUs, and all that CPUs are connected through a common bus. So this is a common bus. So all that CPUs are connected to a common memory. So this is a common memory. So we can also call shared memory. So that means a single memory, it is shared by all the CPUs. So that this is called the multiprocessor system. So here inter-processor communication means one CPU, it is communicating with the another CPU. Okay, through a shared memory. So suppose if the CPU 1 wants to communicate with the CPU 2. So the CPU 1, it places a data or information through the common bus system to the memory. So after some time, the CPU 2 will access that data from the shared memory through the common bus system. So at a time, only one CPU can access the bus. Okay, so that is a inter-processor communication. So the primary use of the common memory is to act as message center. So here this shared memory, it can be acts as a message center. It is similar to the mailbox. So that means see, where each processor can leave messages for other processors and pick up messages intended for it. Okay, so here you can see a mailbox. Okay, so because the shared memory is similar to the mailbox. Okay, so this is a mailbox. So here in the mailbox, it is so let's see. So we have a two processes. One is the sender process and another one is the receiver process. So the sender processor, it will places the data or information into the mailbox, and after that, after placing the data into the mailbox, the receiver process will receive or read the data from the mailbox. So in this way, one process can communicate with the other processor. Okay, so see here. So we have a two process. One is a sending process or sending processor. So sending processor, it structures a request or message or a processor and places it in the memory mailbox. So this mailbox, the sender processor, it is sending some okay, so the status bits reside in common memory are generally used to indicate the condition of the mailbox. So the sender processor along with the information or data, it is sending some status bits also. It is sending some status bits also. So what that status bits represents? So the status bits, it describes whether the mailbox is empty or not. That means it is whether it is empty or whether it contains some data. It specifies that information along with the message is intended to transmitted for. So that means to which processor that message is transmitted. So that information. So these two types of informations are described by the status bits. So first one is the whether the message box is containing is empty or full. After that, and the transmitted message is intended for to which processor. So these two informations are provided by the status bits. Okay. So here, if you come to the receiver processor. So the receiver processor can check the mailbox periodically to determine if there are valid messages for it. So this receiver process, it checks the status bits which are available in the mailbox. So it checks the status bits. Okay. So after reading, so always this receiver process, it has to monitor periodically because whether the mailbox contains the data or not. So if the data is available, then only the receiver process can read from that mailbox. So otherwise, the receiver processor has to wait until the mailbox it receives the data from the sender processor. Okay. So the response time of this processor can be time consuming since the processor will recognize the request only when polling messages. So it is a time consuming process because the receiver processor, it has to continuously monitor the mailbox. So it is a time consuming process. Okay. So that's why in order to overcome this drawback, we are providing another technique that is called interrupt. So okay. So here the mailbox, so when the sender processor, it places the data into the mailbox, and after that the receiver processor will read that information from the mailbox. So suppose if the sender processor and receiver processor, if they try to access the data from the mailbox at a time, then some conflicts will occur. Okay. So a more efficient processor is for sending processor to alert the receiver processor directly by means of interrupt signal. Okay. So that means, see here. So in this mailbox scenario, the sender processor, it is sending the information or data to the receiver processor. So when the sender processor, it is sending the data, along with the data, the sender processor also sends a interrupt signal to the receiver processor. Okay. So when the receiver processor, so this sender processor, it is sending a request, sending a interrupt signal to the receiver processor. So when the receiver processor, the interrupt received, then it can come to know that the mailbox contains some valid data, so that the receiver processor can read the data from the mailbox. So by using the interrupt signal, here the time is saving because the receiver processor no need to periodically check the mailbox. Okay, so that is a advantage with the interrupt signal. Okay, so this can be accomplished through a software initiated interprocessor interrupter by means of instruction in the program of one processor, which when executed produces an actional interrupt condition in a second processor. So one processor will send a interrupt signal by means of executing some interrupt signal, so that the interrupt signal will be sent to the other processor. So this alerts the interrupted processor of the fact that a new message was inserted by the interrupting processor. So when two processors trying to use the same shared memory or any resource, then the conflict will occur. So already just before we have seen. So this is a mailbox. So if the sender processor and receiver processor, if they are trying to access the mailbox at the same time, then some conflict will occur. Okay, so the some conflict will occur. Okay, so these conflicts will be overcome by using a synchronization concept. Synchronization. By using synchronization, then we can avoid such type of conflicts. Okay, so you can understand this scenario with one problem that is called producer consumer problem. Producer consumer problem. That means we have a two process. One is producer process, and another one is the consumer process. Okay, so these are the two processes, and we have some memory. So the producer process will produces the data into the memory. Okay, after that the consumer process will read the data from the memory. So these are the two processes: producer process and consumer process. So if their data transfer rates are different, that means if the producer is if their data transfer rates are not same, then some conflicts will occur. Suppose if the producer process is transmitting the data at a faster rate, but if the consumer process it is receiving very slowly, then what will happen? So that means more data is stuck in the memory or pipeline or mailbox. Okay, so that more data will be accommodated inside this mailbox. Okay, so that means that is a overloading problem. That is a overloading problem. And another scenario, that is the producer process is producing the data at a lesser rate, but the consumer process it is consuming at a faster rate. That means the consumer process it doesn't have enough data to read from the mailbox. So this is also it will create a problem. Okay, so because of this their data transfer rates are not same, then it will this type of conflicts will occur. Okay, so in order to overcome this, we are using a concept synchronization. So synchronization. So by providing proper synchronization, then we can avoid this conflicts. And then come to the what is interprocessor communication. So interprocessor communication is used for interchanging useful information among various regions in one or more processes. This communication could involve letting another process know that some event has occurred or transferring of data from one process to the another process. So interprocessor communication, that means two or more processes are communicating with each other. Now coming to synchronization in interprocessor communication. So synchronization is an essential part of inter-process communication. So already we have seen what is the necessity of synchronization. So this synchronization is it is an essential part of the inter-process communication. So the synchronization it plays a crucial role in inter-process communication. So It refers to a case where the data used to communicate between processors is control information. So it is either given by inter-process control mechanism or handled by the communicating process. So it is required to maintain the correct sequence of process and to make sure equal access to shared writable memory. So multiprocess systems have various mechanisms for synchronization of the resources. So in a multiprocess system, we have different mechanisms in order to provide the synchronization for the resources. So mainly we are using these two types of the methods. So first one is the mutual exclusion and second one is the semaphore. So by using these two, we can provide some mechanism. We can provide some synchronization. So first one is a mutual exclusion. So what is mutual exclusion? So mutual exclusion, it requires that only single processor thread can enter into the critical section one at a time. This also helps synchronize and prevents the race condition by creating a stable state. So suppose if you consider a multiprocessor system. So in multiprocessor system, we have more than single processor. That means two or three like that processors are there. Okay. So this is a CPU 1, CPU 2, CPU 3, and this is a shared memory. So see here. So here this is a resource. Memory is one of the resources. So this resource, it should be accessed by only one CPU or one processor at a time. Okay. So see here. Suppose if the first CPU wants to access the shared memory, then the first CPU will access the memory. So after accessing the CPU 1, then it will releases the shared memory. Then only the second or another CPU will access. That means only one CPU or one processor can access the resource at any point of time. So that means based on the mutual exclusion. So one processor based on the mutual exclusion, the resources will be accessed by multiple processors. So that is called mutual exclusion. And also you can see another way. So the mutual exclusion, it requires that only single process thread can enter into the critical section one at a time. So what is critical section? So we have a program. Okay. So we have a program. So critical section is a section, a sequence of instructions repeatedly using. So that is called critical section. That means a set of instructions that are accessing repeatedly. That is called critical section. Okay. So that means only at any point of time, only one process can enter into this critical section. Suppose if you have multiple processes, P1, P2, P3. So like that, three processes are there. So these three processes, they cannot access or they cannot enter into the critical section at the same time. Only one after. They can access one after another. Suppose if the P1 entered into the critical section, after the P1 process released or come out of this critical section, then only the P2 can enter into the critical section. So that means this has happened because of the mutual exclusion. And coming to the second type of the method to provide the synchronization is the semaphore. So semaphore is a non-negative integer. It is a non-negative integer. That means the semaphore, it contains some positive integer like some 1, 2, 3 and so on. That includes 0, but it doesn't have any the negative values. So it doesn't have any negative values. It contains only either 0 and its positive values 1, 2, 3, 4 and so on. So mainly this semaphore is used to solve the critical section problems by acting as a signal. So the main use of this semaphore is the it is used to solve the critical section problem. So just before we have seen the critical section problem. Suppose if the 2 or more processes are trying to enter into the critical section, then it will be a problem. Okay, so by using this semaphore, then we can overcome the such type of problems. So semaphore is a type of variable that generally controls the access to the shared resource by the several processes. Further, semaphore it is divided into two types. One is the binary semaphore and another one is a counting semaphore. So let's start with the binary semaphore. So this binary semaphore we can also call the mutex lock. We can also call mutex lock. So in this type of semaphores, the integer value of the semaphore can only be there either 0 or 1. So binary. So by means 2. So 2 numbers. So here we are using 2 numbers, either 0 or 1. So using this 2 states, we can represent the semaphore. So if the value of the semaphore is 1, it means that the process can proceed to critical section. So already we have seen we have a critical section. So if the semaphore value s is equal to 1, it means the process can enter into the critical section. Okay. And similarly, if s is equal to 0, that means if the semaphore is equal to 0, then the process cannot enter into the critical section. Okay. So here you can see when the process is using the critical section of the code, we change the semaphore value to 0. Okay. And similarly, when the process is not using it, then we can allow a process to access the critical section. We can change the value of the semaphore to 1. So that operation you can understand with this diagram. Okay. So see here. So we have we have a resource. So that is one of the state is available and another state is unavailable. So if the initial value of the semaphore is equal to 0, that indicates that the resource is unavailable to the processes. Similarly, if the semaphore initial value is equal to 1, that means the resource is available to the process. And when the semaphore value is equal to 1 or it is in the state of the available, then we can change it to the unavailable state by releasing the value. So that means that the value will be equal to 0. So initially it is 1, but we have make it equal to 0. So that means changing from available to the unavailable. And suppose if the resource is unavailable, but we can make it available by releasing the value by releasing the resource. Then the value will be equal to 1. So if the value is equal to 1, then that means the resource is available. If the value is equal to 0, then that means the state of the resource is changing from available to the unavailable. So that is a binary semaphore. So in binary semaphore, we have only two values. One is either 0 or 1. So 1 represents it is available and 0 represents unavailable of the resource to the process. And coming to the second type, that is a counting semaphore. So counting semaphore or signaling integers. These are the signaling integers that can take on any integer value. It can take any integer value, like it can be a 1, 2, 3 and up to n value. So using these semaphores, we can coordinate access to resources, and here the semaphore count is the number of resources available. Okay, so suppose if the s is equal to 5, s is equal to 5, so that means that the available resource will be accessed by 5 different processes. Okay, so if the value of the semaphore is anywhere above 0, that means greater than 0, the processes can access the critical section or shared resources. Okay, so the process can access the critical section or resource only if the semaphore value is above the 0. That means 1, 2, 3, 4 and so on. But if the semaphore value is equal to 0, then the process cannot enter into the critical section or it cannot access the resources. So if it is equal to 0, then there are not any resources that are available for the critical section, because the critical section is already used by some other process. So that's why that is unavailable. And counting semaphores are generally used when the number of instances of the resource is more than 1 and multiple processes can access the resource. So here you can see the counting semaphore. So suppose if the initial semaphore value is equal to 0, initial value s is equal to 0, s is equal to 0 means unavailable. So that means no process can utilize the resource or no process can enter into the critical section. So that is unavailable. Suppose if it is unavailable. Okay, that is one case. Second case is if the semaphore value is greater than 0. So greater than 0 means it could be a 1 value, 2, 3, 4, 5 and so on. Suppose if its semaphore value is 3. So that means the resource, it can be accessed by 3 processes. Okay, so that means the resource, suppose we have a memory. So this is one of the resources. So this memory, it can be shared or it can be accessed by 3 processes: P1, P2, P3. So these are the 3 processes that wants to access the memory or resource. Okay, so when s is equal to 3, so it indicates 3 processes can utilize the same resource. Okay, so suppose if so currently suppose if the one P1 only, it is utilizing the resource. So that means one process is utilizing. Then what will be the semaphore value? That means already out of the 3, one is utilizing the resource. So that means its count will be decremented by 1. So initial count is 3. Now the updated count value is 3 minus 1. So that means 2. So that means now the updated count is equal to 2. So that means only the remaining 2 processes can utilize the resource. Okay, now suppose P2 also utilizing the resource. Then the count again 2 minus 1. That means only 1. So remaining only 1 process is there. One process can access this resource. And if P3 also utilizing, then 1 minus 1, then that is equal to 0. So what 0 indicates? That means the resource is unavailable to the other processes. So that means the change of the resource the state of the resource, it is changing from available to the unavailable. Okay. Similarly, suppose so at the instance, so all the three process utilizing, so that the semaphore value is equal to 0. Suppose if the process P2 it released the resource, then what will happen? So that means here what is available? One more process can access that resource, so that the semaphore value will be incremented by 1, because one P2 process it released the semaphore, it released the resource. Okay, so that what is the initial count here? 0. So 0 is equal to 0 plus 1. So that updated value will be 1. So now the count is 1. Semaphore value is 1. S is equal to 1. So that means one more process can access this resource. Okay. So this is a counting semaphore. So in this way, the semaphore value can be used. And coming to the approaches of the inter-process communication. So using some approaches. So the following, these are the different approaches to implement the inter-process communication. So what are those approaches? First one is the pipes. Second one, shared memory. Third one, message queue. Fourth one, direct communication. Next one, indirect communication. And next one, message passing. Then FIFO. So these are the different approaches to implement the inter-process communication. So this is an inter-process communication. So we are dividing into these pipes. So message queues, first in first out, shared memory, message passing, direct communication, indirect communication. So let's see one by one. So first one is a pipe. So pipe is a unidirectional data channel. It is a unidirectional data channel in which the data can be moved in only one direction at a time. So that means we can transfer the data only in a unidirectional at a time. So that means see here, for standard input-output methods, we can use two such pipes to create a two-way channel to send and receive the data in two processes, that is input and output. So using one pipe, we can only transmit the data in unidirectional way. So that means only from sender to receiver. But if you want to use it for a two-way communication, then we have to use the two pipes. Two pipes. That is, for one pipe is used for input and another pipe is used for output. So by using two pipes, then we can establish a two-way communication. So these are the used in all POSIX. That means a portable operating system interface. Portable operating system interface. So this type of pipes we are using in POSIX systems and various versions of the Windows OS. And coming to the second one, shared memory. So shared memory is a type of memory that can be used or accessed by multiple processes simultaneously. Okay. Suppose if the in a multiprocessor system, we have multiple processors. Suppose 2 or 3 or 4, 5, and so on. So all that process simultaneously they can access this shared memory. So the type of memory is called shared memory, and this is done for a reason. A process can communicate with each other. So why we have developed this shared memory? Because for the communication purpose, because inter-process communication. Because so in a multiprocess system, we have multiple processes, P1, P2, P3, and so on. So one processor needs to be communicated with the another processor. So mainly this shared memory is used for for the communication purpose, in order to communicate the process with each other. So that is why almost all POSX systems and Windows operating systems use the shared memory. And coming to the third type of method, so that is a message queues. So multiple processes can write the data to the message queue even without connecting. Okay, so messages are stored in queue till their recipient retrieves them back. Messages queues are helpful for inter-process communication and are also used by most operating systems. So these are the message queues. So the producer, so this is a producer consumer scenario. So this is a producer process and this is a consumer process. So the producer process, it will produces the data and that produced data will be placed in the message queue. Will be placed in the message queue. And that produced data, it will be available in the message queue until the consumer process received that. Coming to the fourth type, that is a message passing. It is a mechanism that process synchronization and communicates with each other. So what is message passing? So message passing is a mechanism. So by using this mechanism, the process synchronization and communicates with each other. But using this mechanism, the processes can communicate without shared variables being restored. So generally the inter-process communication mechanism is provided by two operations. One is the send a message and another one is a read message. So by using these two, the message passing system can be implemented. So here you can see a diagram that represents the message passing system. Okay. So see here. So in a shared memory, we have multiple processes are there. So let us assume this is a process P1, process P2, and this is a kernel space. Okay. So here one process, let us assume this process P1, it is communicating. So it is sending the data. It is sending the data from the process P1 to the kernel space. Similarly, from the kernel space, the data is transferring to the process P2. So in this way, by using this message passing technique, we can transfer the data from one place to the another place. And fifth one is a direct communication. So generally a link is established between two communication processes in this type of communication. So however, only one link can exist in every pair of communicating processes. So in direct communication between the source and the destination, we have a link. A link will be established. Using that link, that two processes can be communicated with each other. So that is a direct communication. And coming to the indirect communication. So what is indirect communication? So when processes share a common mailbox, then only indirect communication can be established. So just before we have seen about the mailbox. So we have a mailbox. So here we have some processor P1, processor P2. So processor P1 will send a data to the mailbox. After that, the P2 will read the data from the mailbox. So these two, both the processors, they cannot access the mailbox at a time. So that is called, that is a indirect communication. So that is a indirect. So direct communication is the time at which the P1 transmits the data. By that same time, the P2 should read. That is a direct communication. But here in the mailbox scenario, both the process are not accessing the data from the mailbox simultaneously. So that's why it is called indirect communication. So the nature of this shared links could be unidirectional or bidirectional. And coming to the last one, that is a FIFO. So that means first in, first out. So it is the general communication between two unrelated processes. It is also considered full duplex, which means that one process can communicate with another and vice versa. Okay. So in this lecture, we have discussed about what is inter-process communication and different techniques or different methods that are used in order to implement the inter-process communication. And also we have seen what is synchronization and the different synchronization mechanisms in order to implement inter-process communication. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.